The second speaker is Sumilan Banerjee from IIS of India. So let's welcome Sumilan. Please.
Okay. Okay, thank you, Jedong. And of course, thanks the organizer. So you can hear me clearly, right?
Yes, yes.
Okay, thank you. Yeah, and I thank the organizer for giving me opportunity to talk here. And I really like this workshop, especially I mean it has people from various different fields which we generally don't hear about. So great. I mean, hopefully we will be able to meet sometime in future personally. So anyway, so I'll be talking about this topic. I have changed my title of the talk a little bit, but it's essentially the same talk. So I am at the Center for Condensed Matter Theory, Department of Physics, Indian Institute of Science, which is in Bangalore, India. And yeah, I mean, so this is so let me start by thanking my collaborators, acknowledging the collaborators. So the work that I'm going to talk about, mostly done by these two people who are graduate students in our institute, in our department, Surojit and Lokesh. So I might not have time to talk about some work by Shivaram, who is another graduate student. And the thing that I'm going to talk about started from some work which I did some time ago with Ehud Altman in UC Berkeley. So yeah, so that's the thing. Okay, so let's start very basic. So I'll be talking about, as the title suggests, I'll be talking about many-body quantum chaos. So of course, the kind of many-body quantum chaos I'm going to talk about, the characteristic of many-body quantum chaos, I mean, it has many different definitions, and it's not even clear whether they're somehow connected or not. So I'll take this particular one, which essentially comes from a very classical notion, the classical old notion of single particle chaos, effectively, right? So which defines chaos in terms of this classical trajectories diverging away from each other if they start from some initial condition which is slightly away. And you typically measure this chaos in this case using this Lyapunov exponent in some linear stability analysis regime, which is given by this exponential growth. And essentially there is a time scale which is determined by this initial difference, which is roughly this T star, over which I mean, this quantity grows to order 1. And the standard examples are, of course, all these beautiful billiards that are chaotic and not. So now, what is the specific definition of the quantum chaos? Again, it's a very well used definition nowadays, and that is basically this this correspondence, which is somewhat ad hoc, of course, that you write this object which defined your Lyapunov exponent in terms of a classical Poisson bracket at 2 different times, and then just somewhat ad hoc manner say that, okay, I mean, in some semi-classical limit, you just make it a commutator. Of course, you have to keep the dimension proper, so you divide by this IH bar, etc., and you get this this object. So now this object, of course, I mean, you can look at this object in many different ways. So one way to look at this object is to look it in terms of some kind of correlators. And of course, if you just take an quantum expectations with respect to some thermal average or some initial condition or some wave function, like a Gaussian wave packet or something, then you just don't take the average. I mean, you square it, because if you just take the average, it will just give you the standard 2-point correlators, which of course we know that it doesn't grow, right? So you square it, and the thing is that I mean, at least for the semi-classical systems, which has some small h bar in some sense, it has this form which essentially determined by the same classical Lyapunov exponent in this limit. And the idea in recent times, mostly starting from some work by Maldacena and in high energy physics and Kitaev, is just to generalize this object for some many body systems, and let's say some spin operators or something, some local operators A and B, and you just generalize this definition of this out of time order commutators. Typically, you take operators which initially have different support, and so they commute, anti-commute or commute, okay, depending on whether they're fermion or bosons. So now there is another part which is also used, sort of equivalent more or less, which is that one part of this commutator square, which is called this out of time order correlator, and this quantity, so this out of time order commutator, it grows, and thus similarly this out of time order correlator reflects the same growth as a decay, okay, of this particular form, and this is also called scrambling. And of course, we have heard many talks here which talks about other characterization of thermalizations, which happens, of course, at much longer time, and there could be some connections between these two, but these are not completely clear. I will not be talking about such characterization at all. So I'll be only focusing on this. So now, of course, the kind of systems that we'll be talking about is this quantum systems, and how quantum effects come into this type of things. So one way, of course, the quantum effects comes, which is known even from non-interacting systems, weakly interacting systems, and even for many-body systems in this more recent work, is that, I mean, if you look into this out of time order correlator, commutator, then you know that there is a regime over which, at least for this kind of semi-classical systems, or system with some kind of semi-classical limits or weakly interacting systems, it grows with some exponential growth. And then eventually this interference effect comes, either many-body interference or not single particle interference like weak localization effects, and ultimately saturates this growth in most of the cases. So now, and this happens, this crossover happens at a time scale which I'm calling T star, or its unphased time. So, so generally the kind of system I'm going to consider, there I'm going to send this time to very large time. Basically, this time is controlled by this small parameter, which is some quantum parameter, which could be h bar or could be 1 over n. And this is the model that I'm going to talk about, where there is a 1 over n parameter, and then this log n is very large. And so essentially, I'm throwing this quantum interference effect in the OTOC out of the window and only focusing on this region. But even in this region, what I'm going to ask is that even in this region, are there some quantum effects which is discernible? You can see this effect in how it changes lambda L. Okay, so note that I have sent this unphased time, so those kind of effects are not there. I'm just going to talk about quantum effects on lambda L. And in this regime, the thing by definition of, or by taking these models, this thing is growing. Okay, so another aspect which I'll probably not be able to talk about is, which is also important, which is this ballistic spread of chaos. I mean, in this case, I'm talking about a chaotic system, so I can say ballistic spread of chaos. In general, it's some operator spreading, which also define another important quantity, which is this butterfly speed. For example, shown here is this kind of light cone. And actually it turns out that this butterfly speed or this kind of ballistic spread exists even in systems which are diffusive or even anomalous diffusive. Okay, so in fact, if I'll not get time, but this picture is for a Kosterlitz-Thouless phase in a classical XXZ model, large S XXZ model, and where you see it has anomalous diffusion, and still you have this light cone spreading. Only effects of this low temperature phase you see is that there is an onset of this spreading, which is actually temperature dependent and diverges with temperature. I'll probably not be able to discuss this. Okay, so now let's just come to why care about this. I mean, why care about all this? Only Lyapunov exponent, for example, or not more interesting interference effect which I'm throwing away. So one reason is, even in this regime where I have sent this unphased time to be a very large value, it seems which looks like a very classical regime, but this is a regime where we have a very remarkable conjecture bound of this quantity lambda L, which is very strange, because I mean, this is sort of a classical regime, but this is probably the only well established quantum bound of rate of some kind of thermalization that we know. That the quantum mechanics put bound on this quantity, and is given by this upper bound, which is 2 pi kBt by h bar, which is this Maldacena-Schenker-Stanford bound. And indeed, there are systems which actually satisfy this bound. System meaning there are, of course, models, or I mean, they probably exist in nature also. And these are called these fastest scrambler. So this is one thing, and there is some kind of universality, some fundamental quantum bound, almost like some uncertainty bound or something like that, although it includes some many-body physics, this temperature of some thermal eigenstates or some thermal state that involves here. And then the second thing is that it turns out in some systems, some strongly correlated system, there is this quantity Vb square by lambda L, which has dimension of diffusion constant, actually indeed equal to the diffusion constant. Okay, so that also, I mean, there is no proof about this in general or in kind of system it happens, but that also looks intriguing because, I mean, this quantity as such, there is no reason connected to diffusion constant, which is calculated in a completely different 2-point correlator, some density correlator, etc. Why it is related to this, right? So there is some relations between transport and chaos. So these are many questions that we have, that what is the connection between chaos and transport? What is the role of chaos in thermalization, late time chaos, RMT chaos, etc., entanglement growth? And also there are some questions which are probably relevant even for very realistic systems like metals, that where you ask that whether there are such bounds even for transport scattering rates. And indeed there are, of course, experimental evidence of a wide variety of systems with completely different mechanism of transport some seems to satisfy or some follow this kind of thing, which is called Planckian dissipation, where this scattering rate seems to follow this ABT by h bar, some kind of universal value dependence. Okay.
Sumilan?
So yes.
So you're in the formula for the bound on lambda L, the upper bound is inversely proportional to the Planck constant. So
that's right.
Does that mean in the semi-classical limit, there is a chance to have an infinite Lyapunov exponent?
Exactly. Right. Yeah. So if you take the bound, so in fact, this is one of the things I'm going to talk about, right? I mean, yeah. But if you literally interpret the bound, what you said is correct, right? So
okay.
So I mean, it just says that the classical system can have any Lyapunov exponent, which seems okay, intuitively okay. I mean, why should they have such bound? Yeah, but that's right. Okay. Okay. Okay, so let me just rest of the talk. So I'm mostly going to talk about this particular problem, which is in the second point here, which is this, which is somewhat related to the Zedong questions. I'm not going to answer this question. We'll see why, but we'll see. I mean, how h bar when varies, what happens to this lambda L. So this is the main thing of the talk. But to set the stage, I'll talk about some of the chaos computation in large N models. The famous one, of course, the Sazdev-Kitaev model, and some related models. And I'll probably not get any time to talk about this relation between transport and chaos for anomalous diffusion, etc., that I mentioned. But if I get time, or if somebody has question, I'll be happy to discuss. Okay. So let me just, to set the stage, let me discuss this Sazdev-Kitaev model a little bit. I'm not going to talk about it as a model, interacting model of fermions, which are interacting with infinite range interaction, all-to-all interactions, this 4 fermion term, which is random, drawn from some Gaussian distributions. You have n sides, and these fermions resides on n sides. If you like, you can control densities with a chemical potential. And so this is the model, and you have certain scaling with n to make it thermodynamically meaningful. Okay, so that is the model. So now the model, of course, the main thing is that this model is actually solvable in a very simple way, simple field theoretic way. I mean, sort of minimal level field theory, and it gives. But the main thing is that even though it's such a simple thing to solve in some sense, it gives this non-Fermi liquid ground state at low energies. And the second thing, of course, which was pointed out by Kitaev, that this model exactly satisfies this bound, which you can extrapolate at asymptotically low temperature using some out of time order correlator in terms of these fermionic operators. And this, as I said, is the upper bound to chaos, is also satisfied by some black holes or black holes in general with like semi-classical gravity, quantum with semi-classical limits, etc., which I don't know much about. And that's the reason Kitaev thought about this model to make a model of solvable model for holography. Okay, I'm not again going to talk about that. So before going into some results on this, let me just mention a bit that kind of way you calculate things here in this model, meaning the lambda L that we are going to consider in the large n limit. Remember, I said that I'll push this limit of unphase time at very large time by n, and then I have this lambda L to be concerned about. So what we do is a very simple step, just to state. I mean, you essentially write down Swinger-Dyson equation. Due to the disorder averaging as n tending to infinity limit, you only have this very standard self energy that only contributes in this limit. So you can basically do everything. I mean, even you have asymptotically low energy solutions analytically, and you can of course always solve it iteratively in a computer. So that's quite easy. And you then calculate this 4-point correlator, which in the leading order in 1 over n gives this chaos, okay, e to the power lambda LT, which only comes in 1 over n, and that's why you get this log n of the scrambling time. Okay, so that's how you push this time to very large value. So to do the calculation, you do some standard things. I mean, maybe slightly non-standard, but it has become standard now. You slightly different Keldysh contour. Typically, we see Keldysh contour with 2 branches. Here, it turns out you have to. It's better to use 4 branches. Makes life easier. And then in this model, you can write this 1 over n piece as some ladder series, which also looks very simple, and ultimately end up with a kind of a kernel equations, which gives this OTOC in terms of the OTOC itself, sort of like an eigenvalue equation, which you solve. Okay, and in the input to this kernel from this large n calculation is the Green function. Okay, so this is the general procedure, and the kind of model I'm going to talk about. This is the procedure I'll follow. Okay, so let me before going to this main topic, which is about this crossover of this dependence on H bar, let me just talk about one model which sort of gives the motivation of this type of studies. So the question here was that, let's say you take the SYK model, can you do some non-trivial modification of the model where basically, I mean, you can make, so as I said, that this lambda maximum value in this model. So can you somehow change this maximum value to something smaller? I mean, ideally, if you want to make it 0, that would be like some kind of MBL or some mimicking some toy model of MBL, which of course in this large n calculation you cannot really do, but you can make it smaller. Okay, and so that was the kind of question we had, and it turned out that you can do it. I mean, in somewhat non-trivial manner. I'm not discussing what I mean by non-trivial manner here. But the point is, it turns out that you have to add some extra set of fermions, some lead fermions or peripheral fermions, which are on their own non-interacting, but they're coupled by some quadratic hybridization term with this SYK fermions. And there are n sides of this SYK fermions and m sides of this auxiliary fermions. And the way you take large n limit is that you keep this ratio of m by n fixed, which we call P, and take n to m, n and m both going to infinity. And you put some terms here so that everything is well defined in this way of taking limit. Okay, so let me just mention what happens here. So what happens here is that you find that, in fact, as a function of this parameter P, which is this ratio of m by n, you actually get a transition exactly at P equal to 1, which doesn't depend on any parameter of the model. This is sort of universal. I mean, you will always get it at P equal to 1. And you get a transition from a non-Fermi liquid to a Fermi liquid. And indeed, you get a transition where this lambda L goes from 2 pi kBt by h bar. I'm removing kb and h bar from this here, taking them to be 1. So you get a transition from this 2 pi kBt by h bar, which is this entire phase at low temperature is this maximally chaotic, into some Fermi liquid which has this T square. And this T square, of course, reminds you of quasi-particle scattering rate. Indeed, these are determined by quasi-particle scattering rate in a Fermi liquid. Okay, so this is how you change this thing. And again, here some kind of quantum fluctuations is at play, namely that when you couple this, there is some kind of hybridization between this C and psi. And so this model is almost similar to this multi-channel Kondo model, the effect of screening and hybridization is some sense able to change this lambda L drastically even within this unphased time regime.
Sorry.
Okay, now let me do the yes.
Sorry, question. Can you go back?
Yes.
The fact that you take V, I mean, V is another random term, right? Is another VI alpha.
Yes, yes.
Is it crucial
Right.
for the physics or for the computation?
It's not crucial for the physics, no.
Okay.
Not for
But
computation also. Yeah.
Okay. Okay.
Yeah, you can. Yeah. Yeah. Right. I mean,
Okay,
sorry, V. Okay, so you mean random? Yeah, random is required for computation, right? Yeah, yeah. Yeah. Sorry.
Right, but
Yeah,
for
I mean,
the
you
physics,
try to make
you will
it
see the
all
same
the-
physics, right?
more or less, yes, yes. Yeah, I think.
Okay. Okay, thanks.
Okay, so now let me come to this point, and this is sort of the topic that I wanted to talk about, which is related to this Zedong question, which Zedong pointed out. That if you now, of course, so one problem with all this, as we can understand, right? I mean, we are talking about quantum bounds, etc. But I mean, it seems that this is very classical concept, right? I mean, ultimately, the original concept comes from classical physics, and then you went into this somewhat ad hoc way from Poisson bracket to commutator, and then you define some correlators, and then you are talking about all these things. So you can now trying to go back to classical, right? I mean, so you come from classical to quantum, and you, let's say, want to go back to classical, and then try to ask that what is really happening in between, right? I mean, I went there, but can I really do it in a controlled manner, right? So the thing is, of course, this bound itself, h bar is in the denominator, so it will diverge. So it says that there is no bound classical limit. I mean, which seems okay, intuitively okay. I mean, there could be some deep reason that there could be bound even in classical systems. In general, universal bound, I mean, it seems intuitively okay that you don't have a bound, right? So now, so the bound is trivial in the classical limit, of course, right? But I think the interesting question comes that if you really try to take some system, let's say the SYK model that I discussed, and let's say somehow you can change h bar, right? How? Okay, so that let's not go into that. So let's say somehow you can change h bar, even keeping this n fixed, right? So n I am already keeping very large, but some other parameter. So you can change this, and then the thing is that what really happens? I mean, is it that it will follow the bound? Is it that it will saturate to some value, or it can change, become non-monotonic? I mean, so what is the nature of quantum corrections, right? I mean, that happens. I mean, so that is the question, right? And of course, you can have some systems which starts from away from the bound and somehow start hitting this bound, and then it cannot go above the bound because it's a bound, and so it will change. But then you can ask what is really happening, right? What is the mechanism by which quantum mechanics is putting this fundamental bound? So this is the kind of questions I have, but I mean, I don't know the answer of this. But we take a first step where we take a system which is, of course, away from the bound. It will not close to the bound at all, but still I will discuss that it can have this behavior, that the effect of quantum fluctuations, meaning this h bar, could actually be quite non-monotonic. Okay, so it can go up, it can have something like this, and you can have a quantum systems which can have, in some sense, quote unquote, is more chaotic than the classical one. Okay, so that is the sort of the questions. I have written the questions again here, but here is one thing, that we want something similar to SYK model, ideally SYK model. But the problem with the standard SYK model is that I can't really vary h bar. I mean, these are fermions, so I don't really know how to do. I mean, there are of course some models, spin models, which are related to this. The spin half representation is the SYK, and there you can change, but those are slightly harder models. So I'll take initially a model where you can do a change h bar, but is somewhat simpler. And it turns out that such a model, which is also, of course, also very important in many other aspects, which I'll discuss, is this well-known model which has been studied in a different community, which is in the community of glasses. Okay, so this is this quantum spherical Spinglass model, which comes from the original spherical classical Spinglass model, which is related to also random energy models and things like that. So this is the p spin term, which again you have some random interaction between p spins, and there is some spherical constraint to make the model non-trivial to bound these numbers. And then in this quantum model, what you do, you add like the simplest kind of quantum term that you can add, which is some kinetic energy, and the quantum dynamics is generated by the standard commutation relation. So you take this as position and you take this as momentum. Okay, so in this model you can actually vary h bar continuously, and this model also has very well-known phase diagram which I am showing here. So let me just mention what is the phase diagram is about. So I am plotting some quantum parameter, this h bar in the y-axis and temperature on the x-axis, and this model essentially has two kinds of phases. One is this paramagnetic phase, and then there is a replica symmetry broken Spinglass phase for p greater than equal to 3. So p equal to 2, the model doesn't have this replica symmetry breaking. So, and then there is a transition. The transition becomes first order at low temperature. There is some quantum paramagnetic phase. I'll not talk about that. Okay. So I'm mostly going to focus into this region where you have this classical paramagnet. There is a transition. So there is actually two lines. One is thermodynamic transition, and then there is some ergodicity breaking dynamical transition, which I'll talk a little bit about. And then you go into this paramagnetic phase. Okay, and I'll discuss probably these lines. Now, what is plotted here is this Lyapunov exponent in color, and you can see that this is large Lyapunov exponent. So this model actually sort of has a peak. There is a locus of maxima of Lyapunov exponent, which is actually above this transition over some region here. So in this model, the kind of questions we are interested in to ask is this interplay of quantum fluctuation, glassy dynamics, replica symmetry breaking, and chaos. So although we wanted to only look into quantum fluctuations and chaos, but this model also gives this. And another thing is that this model in this limit h bar tending to 0, which is the limit that we can take at least numerically in this large N calculation, is that it gives also a very important system, at least some aspect of some very important system, which are classical supercool liquids. Okay, so in as an offshot of these calculations, we will naturally get these descriptions of chaos in a classical supercool liquid. So let me just mention this classical supercool liquid very quickly. So these liquids are the supercool liquids where you go below melting transition, you do slowly enough but also fast enough so that you sort of stay in some kind of metastable liquid state. And what happens in real glass formers is that if you measure viscosity, which is related to some relaxation time, they seem to diverge at some finite temperature. At least they seem to go to a value beyond which you cannot really measure this viscosity. Okay, so that's how this glass transition is defined, and they can diverge very fast. Okay, so that's the physics of this classical glass supercool liquid glasses. So now looking from the point of view of quantum correlation functions, so the correlation function has some interesting behavior. Sorry, Jedong, how much time do I have?
You have 2 minutes, but I think you can spend more or less. You can talk until.
Okay, I'll just spend
maybe
5 minutes or 6 minutes. Yeah, thanks. Okay, thanks. Okay, so thank you. So let me just so this is some correlation function, right? So some 2-point correlation functions, and what I'm showing here from this review is the correlation function at high temperature. There you expect the standard Debye type relaxation, some exponential relaxation by some microscopic time scales. But what happens if you lower the temperature? If we go into these regimes, remember this is 1/T, low temperature, then you start seeing this 2-step relaxation. So there is some microscopic relaxation, but then sort of the system plateaus, almost break ergodicity, decays a little bit. In fact, it decays like interesting power laws, we well described by power laws here. And then eventually it decays from the plateau with some stressed exponential, with some relaxation time tau alpha with some exponent beta. Okay, so this is what happens at low temperature. And so basically this 2-step relaxation or beta relaxation with some interesting power law decays. And the theory of this particular behavior is what is known as this mode coupling theory of supercool liquid, which turns out to be mathematically equivalent to this p Spinglass, which was shown by many people long time back. So exactly similar equations like this classical p Spinglass. Okay. So it has some equivalence. Now what happens is, if you continue to lower temperature, either in mode coupling theory MCT or in p Spinglass, at some temperature TD, you actually break ergodicity, and then you don't decay at all, like almost like these MBL systems, you don't decay in this thing. Of course, real glass formers this never happens, but in this theory, which breaks down at this temperature, that you get this ergodicity breaking. And of course, in p Spinglass, it is a true ergodicity breaking. You get this replica symmetry solutions. Okay. So also what happens is that this time scale diverges as you approach this dynamical transition where you break ergodicity. So one question you could ask, that what happens to lambda L inverse? Okay, so does it also sort of diverge? I mean, it can diverge. Lambda L inverse can diverge, right? There is no limit to that. So what happens, right? So when you that's another kind of question. Okay, so now let me just come to these results and then I'll end. So again, I'll not go into the detail of it. It's very similar large N machinery that you write large N equations, some self energies. The only difference is that here you have to take this replica symmetry breaking, I mean replica index explicitly, because you can break replica symmetry, and you do break replica symmetry in this model for p equal to 3. I am showing you have some spherical constraint, etc. So this is the standard thing, and you can, and in this model you can have a dimensionless parameter which is related to h bar. So we actually vary gamma, but write in terms of h bar, which is square root of gamma. Okay. So to solve this equation, again you take some ansatz. So for paramagnetic state, you take the ansatz of replica symmetric and diagonal. This order parameter doesn't depend on the replica index, and it's diagonal. In the Spinglass state, it turns out that there is this called one-step replica symmetry breaking, which is exact. And again, I'll not go into the detail of it. In case you have not thought about it, doesn't matter. I mean, it's some metric structure. You have some matrix which you have n cross n matrix. You break into some blocks, and then the block has certain structure. Eventually, you have to take n tending to 0 limit. Okay. So I mean, these are all well-known techniques in glasses which you follow. So our case, of course, we have to calculate the Lyapunov exponent, and so in the paramagnetic case is very similar to the SYK model, if you wish. It has very similar the ladder diagrams which I showed earlier, and this is the region. Let me focus now that discuss. So I'm now first looking into this region in the paramagnetic phase, where I am looking at a fixed temperature. So temperature varying from here to here. So lower temperature from higher temperature, I am looking into the quantity lambda L as a function of h bar. And remember, the question I want to ask is that whether this limit is all, I mean, whether this dependence is always non-monotonic, meaning always the classical system is more chaotic or not. Okay, and what you see that higher temperature, indeed that's what happens. That typically, I mean, it saturates at some value, lambda L saturates at some value when h bar tending to 0, and it decreases. Okay, as you increase h bar, but as you come close to this dynamical transition, in fact, this thing which I have not discussed yet, you actually see that there is a non-monotonic dependence on h bar. So it's not that, I mean, in some sense, when you go to the classical limit, somehow quantum fluctuations, it's not true that quantum fluctuation always decreases chaos. Okay, so it can actually increase chaos. And this non-monotonic dependence is also seen in temperature. You also, in the paramagnetic phase, remember this is not the glass transition, it's a paramagnetic phase. This region you see actually again a non-monotonic temperature dependence. Okay, so this is what I sort of summarize, so that you have this non-monotonic dependence. So the main message is that you can have quantum fluctuations actually increasing chaos. Okay, so that can happen. It will be completely non-monotonic dependence on h bar. So now the last thing, so we go to the Spinglass phase. So one additional non-triviality in the Spinglass phase is that you have to incorporate this replica symmetry breaking in these ladder diagrams, and it can be done. It turns out ultimately not that hard. and of course you have to take n tending to 0 limit eventually. All those you can do, and with that we look into this region, which is for some technical reason, in case you are not familiar with, called marginal spin glass. But yeah, don't worry about that. It's some spin glass state that we are describing, and in the spin glass state what you find is somewhat opposite. I mean, in general, the spin glass state, what you find in the quantum fluctuation actually always increases chaos, except maybe at very low temperature, a slight non-monotonicity, but generally it increases chaos. So that is the thing. So depending on the phase, you can, I mean, quantum fluctuation can act differently. It can increase or decrease chaos. There is nothing that in a system where you can change h bar continuously, that the classical system has to be more chaotic. Okay, so there is nothing like that. And another thing is the temperature dependence. I have not shown, but we can show that the temperature dependence is actually a power law at low temperature in this spin glass phase, which has this t to the power alpha, which is the alpha is some exponent which varies from 1 to 2, from going from classical to quantum. Okay, and this is some numerical results, the exponent extracted from numerical calculation of Largen, and you see this varies from 1 to 2. In fact, this result in the quantum limit 2, you can actually calculate it analytically. I mean, using certain mapping of this kernel, which I mentioned earlier, to some problem of Postel-Taylor potential in quantum mechanics. And it turns out to be some eigenvalue problem of that potential, which you can solve, and you can show that this lambda L is actually goes like T square, and this T square is of course like Fermi liquid, is some weakly interacting phase, which sort of some kind of quasi particles which are not very clear here. It break replica symmetry. You have some fluctuations around that in some way, which is not completely clear yet. Anyway, for completeness, so we also look into this lambda L as a function of temperature when you cross the transition, and also as a function of h bar when you cross the transition. And the main feature, I think, is that you typically have a crossover. This lambda L doesn't seem to diverge, lambda L inverse doesn't seem to diverge or anything like that, although we cannot really do calculation at the transition due to some convergence issue. But typically it looks like some slope change, a crossover. And there is of course this broad maxima which I mentioned about. Now, last slide on this, let me just mention this broad maxima actually can be related to some physics of this glassy relaxation which I mentioned. And again, this is sort of a correlation, it may be a coincidence. So the first thing is that if you look into correlation function now, like standard spin correlation, autocorrelation function, then indeed you see like this, as I said, the glasses are described by this p-spin glass dynamics. You see this two-step relaxation at low temperature. You have some plateau, weakly decaying thing. There is some oscillation because of the quantum fluctuations, but ultimately it has this slow decay and then eventually a decay over a huge time scale, as you can see. Okay, so you can actually detect where this plateau onsets. Before that, if you extract this time scale by some fitting, what you of course find that this time scale, which is shown over here, is actually diverges at the transition as we expected. And of course, we have seen that lambda L inverse doesn't diverge. It only has some kind of a minima, or in other words, lambda L has a maxima above the transition. Nothing really happens across the transition. So these two quantities are completely, in some sense, unrelated. But what seems to be related is that the fact that you can detect where this two-step relaxation starts onsetting, meaning where this minima, let's say, goes above 0, sort of, I mean, it's a crude definition. And what you find, this remarkable correlation that this onset of this two-step relaxation, when taking as equivalent to glassy relaxation, which onsets above the dynamical transitions, actually coincides with this broad peak in chaos, okay, in lambda L. Okay, so that's basically the thing. So it seems to be that there is some relation, and the most probably the idea is that there are some power law relaxations here, which is very similar to this SYK, where you have this power law thing, and probably these power laws are determining this chaos here. But we don't have analytical understanding. So let me end here, and sorry for taking a very long time. So just to summarize that, we mainly discussed a solvable model where we can change h bar. It's still not ideal. We wanted to look into what happens if you go along this bound, and what happens if you go away from the bound, what kind of quantum effects happens. we are not able to do it right now, but at least it gives some basic start. And of course, we see all this non-monotonic temperature dependence. We don't have a very clear understanding of these quantum processes, or it's just quantum process, or it's just some renormalization of parameters. That also we don't know. But okay, that's all. So okay, so thank you for your attention. I'll stop here, and sorry for taking more time.
Thank you, Sumilan, for a nice presentation. Yeah, is there any question or comment? Okay, Sergey?
Yeah, I have a question. So when I compute the Lyapunov, the exponent or the entire spectrum in a classical system, I would rigorously do this by linearizing the phase space flow around the given trajectory, and then I have some linear equations, which the symplectic equations, which are characterized by some time-dependent coefficients which come from the original trajectory, etc., etc. And things are pretty well defined mathematically there. Is this quantum Lyapunov exponent calculation approach which you presented here on a similar, can we say that it's on a similar rigorous mathematical footing, or is it not the case?
No, not at all. No, not at all. Not at all. So it's not in the same footing, right? I mean, as I said, so the way I started, at least that's what I know. I mean, there are some connections, maybe more rigorous mathematical thing, but generally it started with some ad hoc thing, right? I mean, we went from this del x, del t, del x0, and then went into this, and then say, okay, we look into this. I mean, at least in this type of models, I mean, I don't even know how to calculate the spectrum, right? I mean, Lyapunov spectrum. I mean, probably numerically you can do. There are some definitions in these quantum models also of calculating Lyapunov spectrum, but generally you do it using exact diagonalizations. Again, I also don't think those are also in the solid mathematical footing like what you mentioned for the classical system. So right now, yeah, it's more like, I would say, analogy and some, yeah, I mean, continuation in some, not really.
And the second question, if I may ask, is so you mentioned these supercool liquid mode coupling theories and the such alpha beta relaxations. I hear this for the first time in the context of quantum chaos and MBL and Lyapunov exponents and such. Could you maybe wrap it up again in one or two sentences what the connection between these two phenomena is?
Okay, so sorry, I was actually very fast. So first of all, I think it's a good question. I actually don't know the answer, real connection. So what I showed here is just a correlation, and I don't think this has been discussed, at least in this kind of approaches, large N approaches earlier, as far as I know. So it's not very clear. So one of the connections that people have put, I mean, people from the glassy physics, Kukshan and Busho and those people, I think. So their point is, if you look into these mode coupling equations, you have, first of all, these power laws in those decays. And again, if you look into SYK solutions of correlation functions, they also have these power laws. Okay. Also, these power laws are not a similar footing, but there is these power laws, and also in the edging dynamics in glasses, also there is this thing called reparameterization symmetry. So where you basically reparameterize time by some arbitrary smooth function, monotonic function of time, and that symmetry is also there in SYK and this kind of some of these large N models. So it's not completely clear what is the exact connections between these. These models are very similar in some sense. They are large N models. They're disordered. You get similar type of large N saddle point equations, and often they tend to give this kind of solutions. So again, the connection to chaos is not completely clear. I mean, we have not calculated anything using that kind of picture. Only thing we see is some correlation between maybe where you have this power law correlations, 2-point correlations like spin-spin autocorrelation, with where the OTOC growth rate is sort of very large, or it becomes a maximum. Okay. Yeah.
Thank you. Thank you.
Yeah.
Okay, then next question, David Logan, please.
So, Sumilan, thank you very much for a very stimulating talk. Can I just ask, the specific calculations you've done are large end saddle point calculations, and I'm just wondering, I know it's a very tricky thing to do, but do you have any understanding, even qualitative, of the extent to which your results are robust to fluctuations about the saddle point? I mean,
Yeah, so there are some, good question. So there are actually some understanding of this. I mean, basically based on, so there are actually some beautiful analytical works by many people, but the one I am most familiar with by Altland, Kamenev, and these people, so who can go beyond, so these large n calculations are only valid when your time scale is like going as, I mean, below the time scale going as n, right? And but there are some way to go beyond that time scale, meaning you can go to time scales which is scaling with n, but not, of course, exponentially with n. And these are some calculations by looking into fluctuations around these large n saddle points, analytical results, so where you can map this to some kind of Liouvillean quantum mechanics and all. So there are some things known in this type of approaches. And also other thing is that there are some large scale exact diagonalization people have done using, of course, not direct brute force exact diagonalization, but some Kulob method and things like that, where they have been able to go to sufficiently large system, maybe 30 or 40, I forget. And there they tend to find, when you go to that scale, you tend to find that this lambda L, which is like 2 pi kBt by h bar, you tend to see that it is going towards that thing. So certainly the 1 over corrections, if you are even like n equal to 40, 30, 40, I think is very large. Okay, so if you are looking into standard exact diagonalization, these quantities, Lyapunov exponents, are far away from what you get from large n calculations. But people have pushed it quite far with these numerics, and they seem to approach these large n results in these limits of maybe 30, I have forgotten, sorry. And it seems then maybe this large n calculations, at least if you have large enough n, I mean, not infinite, but large, it seems to have some control. Yeah.
Okay, fine. Thank you very much.
Okay, Lorenzo, please.
Hi, thank you for the nice talk. I have a question. Recently, it has been shown in the same model that you studied that if one takes a quench in each bar instead of varying it continuously, the dynamics always seem to be, the Spinglass phase, the dynamical Spinglass phase, always seem to be stabilized by quantum fluctuations in a quench. What's the connection between this result and your work?
Yeah, actually, very good question. This is something we have been also thinking about. I actually don't know the answer of the question, but so actually, so what, again, I don't remember the exact detail. You are one of the author of the paper, I don't know.
No, luckily not, but I've read it. Is they just turn on turn on or turn off suddenly the quantum fluctuation in Spinglass dynamics, and they see that.
I read the paper. I mean, again, I don't remember the exact detail. That's what I'm asking. In case I'm incorrect, you can correct me. So I think what they find is that, yeah, as you make quantum fluctuations suddenly quench to larger quantum fluctuations, it seems to stabilize this. Okay, I don't know the exact connection. So one thing you can see, so what we study here is this lambda L, right? So now what you can do, you can define some kind of effective temperature using lambda L and using the bound, right? You can sort of say, given this lambda L, this is the kind of, I mean, the temperature, I mean, if this was a maximally chaotic system, this is some kind of effective temperature I could have. And your temperature, thermal temperature somehow has to be larger than that or something like that. Okay, I mean, so there is some arguments by Mohita and these people. So in that sense, what we find that this lambda L increases with h bar. So in some sense, this effective temperature increases, and that may have some relations with the fact that when you increase h bar, somehow you can stabilize the Spinglass phase even at some higher effective temperature, something like that.
But if lambda L increases with h bar, okay, here you have more chaos,
here,
right?
No, so this No, here of course this is a bound, but if you remember in our Spinglass phase, I went over it very quickly. So there actually this lambda L increases with h bar. So that's the general norm. Okay.
Okay.
So in some sense, if you increase h bar, the effective temperature in some sense increase. I mean, it's not completely true because you have to also keep in fact some h bar in the bound. It seems at least with increasing h bar that there is some kind of I mean the system become more chaotic, but it's still still stay in the Spinglass.
Okay, no, because I mean maybe my intuition is wrong, but if lambda L increases and then the system becomes more chaotic, the glassy phase is destabilized, no, with h bar increasing, which is the opposite of what I was thinking too.
No, so that right. No, so so that's the thing. So idea is that you can define some effective temperature, right? And idea is that I think you're okay. Again, I'm not getting it correct, but your system is at some temperature T, right? Which is of course fixed by whatever environment or bath you are using. The idea is that if somehow you have a temperature, effective temperature, which is I forgot. So you have to have, so let's say you, if your effective temperature is lower than this, I think, okay, maybe actually I'm not telling it correctly. So I'll,
maybe we can discuss another time if you want. Thank you.
Yeah, discuss. Yeah, because I'm not sure what I'm saying. Yeah.
Thank you.
Sorry.
Thank you so much.
Good question.
Yeah, okay. I think it's time to take a break. So let's thank Sumilan again. So
thank you.
Yeah, we will resume the session in 9 minutes.